Okay, so in this tutorial what we're going to do is look at some Equilibria exam questions. A lot of students find these a bit tricky, but there is a knack to doing them. It's usually the same point that we always get stuck and can't go any further. So if we can overcome that, then hopefully the rest of it can be worked out relatively easily. I'm going to use a couple of exam questions, past paper questions, from two different exam boards. This is from AQA, June 2013, Unit 4 paper, and it is testing the typical skills that they're looking for at this level. So it gives us an equilibrium, and it's asking us to do some calculations with equilibrium constants and concentration. And the way to keep right with these is to be very clear about what we're talking about. We have concentrations at the beginning before equilibrium, and we have concentrations at equilibrium, and it's these ones that we use to calculate Kc. But quite often what we're asked to do, they tell us, is known beforehand, and if we work through moles relationship, which we get from the equation, we can then work out whatever it is they're asking us from the unknown. And this is a very typical route through any chemistry problem. So let's look at what the question tells us. It's telling us about how many moles of NaCl we have before equilibrium, and then it's telling us at equilibrium, it's telling us how many moles of NO we have. It's asking us to calculate Cl2 and NaCl at equilibrium. Now, it hasn't told us any volume in the question, so we've no concentrations as such. So the first thing we can do is assume that the volume is 1 decimeter cubed, and this will allow us to work directly with the number of moles without having to worry about what the actual concentration is. Of course, if they give us a volume, which they do later in the question, then we have to work out the concentrations, the actual concentrations. So what do they tell us? Before equilibrium, we've got 2.5 moles of NaCl, so let's put that in there. And at equilibrium, we've got 0.80 moles of NO. So let's put that on the at equilibrium side. So we've been asked to work out the moles of NaCl at equilibrium and the moles of Cl2. So this is where we have to use what we know to work out what we don't know. So from our equation, we can see that 2 moles of NaCl form 2 moles of NO, and of course what that means is that 1 mole of NaCl forms 1 mole of NO. And of course the question tells us at equilibrium we have 0.80 moles of NO. And what that tells us therefore is that 0.80 moles of NaCl must have reacted, since it's a 1 mole relationship. So that 0.8 moles of NO has been formed from 0.8 moles of NaCl. And this allows us to work out how many moles of NaCl we have at equilibrium. Because if we started with 2.5 and we know that 0.8 of them have reacted, it's simple subtraction to tell us that 1.70 moles of NaCl are left unreacted at equilibrium. So we can put that directly into our table here. Of course, and the other thing, looking at the equation, we can see that for every 2 moles of NO we get formed, we only get 1 mole of Cl2. So in other words, if we get 0.8 moles of NO, then we get half as many, 0.80 moles of Cl2. and that's what we have at equilibrium. So if we put that in here, okay, so the thing to sort out is using what we have before equilibrium and the mole relationship to work out what we have at equilibrium. And we could go on to calculate Kc at this point if the question asked us. However, this particular question is asking us something different. It's giving us the volume. So if we notice here, we can work out concentrations. It's giving us Kc. And first of all, it's asking us to write out the expression, so we know what calculation to do. But then it's asking for the concentration in this particular equilibrium mixture. And it's given us the numbers of moles of NaCl and NO. So let's write out Kc first. We know this is the product of the concentrations, sorry, the product of the concentrations of the products, mathematical and chemical, 2 moles of NO, so we have to square that concentration of chlorine. So those two multiplied together, that's the products, divided by the concentration of the reactants, which is NaCl. Again, there's 2 moles of those, so we square that. And we can work these out from the information given us. The number of moles of NaCl was 190, and the volume is 15 dm cubed. So we take the number of moles divided by the volume, we get a concentration of 127 moles per dm cubed. And doing likewise, we can work out the concentration of NO by dividing by the volume, and we get 0.057 moles per dm cubed. And lastly, the question is asking us to work out the concentration of chlorine at equilibrium. Of course, it gives us, the question also gives us Kc is 7.4 times 10 to the minus 13. So our next step is to put in the numbers and do the maths. So the best way to do this is the way that you feel most comfortable with. You can put the numbers in and do the working out as you go along, or you can rearrange the equation, or you could, if you're really happy with the maths, do the calculation all at once. That way you're likely to get the least rounding errors and a more accurate answer. But what it doesn't allow you to do is to check through your working later on, to check if you've made a mistake. So here I'm working through the maths at each step until I come down to this simplest form, and then I'll do the calculation at the end. So we have 7.4 times 10 to the minus 3 divided by 0.201 equals the chlorine concentration, which gives us an answer of 0.0367. So just remembering that this is concentration we've actually worked out. If we flip back to the question, just to point out, the question is asking in moles. It's not asking for the concentration, it's asking for the moles. So if this is our concentration, if we remember that the actual volume we had here was 15, so this is moles per dm cubed. So in 15 dm cubed, we have to multiply that by 15, which will work out at 0.54 moles of chlorine. Okay, so here's the last part of that question, where they've just balanced the equation differently. Instead of using the 2 moles, and 1 mole, they've used 1 mole, and half a mole. And what they're asking you to do is calculate Kc here, and then deduce the units. Again, this is something that comes up quite often. So we write down our expression again. This time there's no squared for the NO because it's 1 mole, but since there's half a mole of chlorine gas, we need to raise that to the power of half, and we divide that by the concentration of NaCl. Again, this is not squared, it's 1 mole. So we have our expression. So using the concentrations we worked out in the previous part of the question, if you can't remember what they are, just flip back. Or if you've written them down, have a look back. So it was 0.057 multiplied by the concentration of chlorine that we worked out, 0.00367, and that's to the power of half, divided by the concentration of NaCl, 0.127. Working through the maths gives us 8.6 times 10 to the minus 2. So working out the units, we just put the units into the equation and then do algebra on them. So the concentration of NO is given in moles per dm cubed, and the concentration of chlorine is also moles per dm cubed, but this is all raised to the power of half, and we're dividing that by the units of concentration of NaCl, which is moles per dm cubed. So cross multiplying these cancel out straight away, which gives us straight away here moles to the power of half. We multiply indices here, dm to the power of minus 3 over 2, so minus 3 times a half. So our final answer is moles to the half dm to the minus 3 over 2. Okay, here's another exam question. This is from exam board OCR A, and this is 2013 paper, January 2013. This is has much less structure to it, and it's worth 5 marks. But if we look at what we have got, we have an equilibria, we have some information at the beginning, we have the volume here, and we have how many moles we have at equilibrium, and then it's a straightforward calculate Kc under these conditions. So let's have a look at it. Writing out the equation, 2NO2 gas in equilibrium with N2O4. You might be familiar with this one. You might have seen it in practice in the test tube with, gas syringe with the brown gas. And here we also have the enthalpy change, so for the forward reaction, 57 kilojoules per mole. So writing out our expression for Kc, it's the concentration of the products, so NO4 at equilibrium divided by the concentration of the reactants, and of course there's 2 moles of this, so we have to square that. So if we look at what we've got in terms of the NO2 concentration, we know that at the beginning they put in 4 moles and the volume is 2 dm cubed, so the concentration is number of moles divided by the volume, which gives us 2.0 moles per dm cubed. And the question tells us that the number of moles at equilibrium is 3.20, so again we can use this at the volume is 2 dm cubed to work out the concentration as 1.6 moles per dm cubed. So if we do before equilibrium and at equilibrium, we see that the concentration of NO2 before equilibrium was 2 moles per dm cubed, and at equilibrium the concentration of NO2 was 1.6 moles per dm cubed. So in order to calculate Kc, we need to work out the concentration of N2O4 at equilibrium. So this is where we work out what we do know. We can work out the number of moles of NO2 that have reacted by taking what we started with what we ended up with, and we see that we have got 0.4 moles. And that's that have reacted. So looking at our moles relationship from the equation, we can see that 2 moles of NO2 forms 1 mole of N2O4 when it reacts, which of course then means that 1 mole of NO2 will form half a mole of N2O4. But what we actually had reacting was 0.4 moles of NO2. So that's how many that have reacted. So we can see that that's a half times 0.4, which equals 0.2 moles of N2O4 that have been formed. And that is of course per decimeter cubed. So if we put those concentrations into the expression for the equilibrium constant, then do the maths, we end up with 0.2 divided by 1.6 squared, and that will work out as 0.78. And let's work out the units. So we have concentration of N2O4 on the top in moles per dm cubed divided by moles per dm cubed. It's NO2 squared. So we're multiplying these by themselves. So this will cancel out with that, which will leave us with the units of moles to the -1, because this is 1 over moles per dm cubed. So we change the sign of these, moles to the -1 dm cubed. Okay. So again, the trick with these is to identify the before equilibrium and the at equilibrium so we don't get confused, and we work out what we know and we use that with the equation to work out how many moles of the concentration of what we don't know at equilibrium. It's usually the style of these questions. But this is the key thing here, is to figure out what's before equilibrium and what is at equilibrium. So here's the mark scheme for that particular question, and if you have a look, you see that it's 4 marks for the calculation and 1 mark for the correct unit, so that is quite useful. Also important to notice ECF, error carried forward. So if you do make a mistake, the best thing to do is to keep going, because if you make a mistake up here but you've done the rest of the question correctly, they do allow you some marks